Now that we have the basics of how to work with vectors, which gives us a way of talking about objects in 3 dimensions, it's time to look at lines and planes. So in this lecture, we're going to focus on looking at lines in 3 dimensions, and it turns out we have 3 different ways of expressing a line in 3D. So to start off, let's think about what we know about lines in 2 dimensions. If we have a line on the xy plane, we can specify it given a point and a slope. So for example, if we know that the point 1, 1 lies on our line and that it has a slope of 2, we can plot the point 1, 1, and the slope of 2 means that for every 1 unit in x, you need to go 2 units in y. So if we wanted to find another point on this line, we could start at the point we know that is on the line, which is 1, 1. We could go over 1 unit in x, 2 units up in y, and that would give us another point. And if we wanted to, we could connect these dots and we'd end up with our line looking something like that. And if we wanted to work out the equation for this line, we know that the equation for a line is y is equal to mx plus c, where this m is the slope. So for our line, we know that this is going to be y is equal to 2x plus c, and we know that this c over here is the y-intercept. So when we've got our equation y is equal to 2x plus c, we're going to sub in the point 1, 1, which gives us a value for x and y, and that'll help us solve for c. So we've got 1 is equal to 2 times 1 plus c, and if you solve this, you'll find that c is equal to minus 1, which corresponds to the value that we saw in our drawing over here. That's our y-intercept. So finally, our equation for the graph is y is equal to 2x minus 1. So the key thing to take out of this example is that in order to specify this line, we needed 2 bits of information. We needed a point on the line, and we needed to know the slope of the line. Now you've studied other ways of calculating equations for lines, but in order to talk about 3D lines, this is the form that we're going to use. So we're going to use the same basic idea to describe a line in 3 dimensions. So here we've got the line that we're trying to find an equation for. And what we're going to do is we're going to specify a point on the line, which we're going to call P0. And this point P0 has position vector R0. And then instead of using just a single number to describe the slope, we need to specify the direction. And for that we can use a vector v. So I'm going to show the vector v starting from the origin, but remember we can move vectors wherever we need them to. Then I claim, and we're going to have a look and see how this works, that any point on this line can be written as xyz, so that's the point or the position vector of the point. So this corresponds to the y if you're looking in 2 dimensions. So we've got the point on the line is going to be equal to R0, which is the position vector of the point on the line, plus some scalar multiple of the direction vector. So let's just be clear here. This R0 is a constant. It's the position vector of some point on the line. This v over here is also constant. It works like the slope, but it's the direction. and the things that vary are the values of x, y, and z, the coordinates of points on the line, and the scalar value t. So how do we get the points on the line? Well, we already know one point on the line, which is this point P naught. If we want to get any other point, then what we do is we start at P naught, because we're starting off at the position specified by R naught, which is the point P naught, and then we're going to add some multiple of our direction vector v. So we start at the origin, we head to the point P naught, and then we're going to add some multiple of v. So in this case I've added plus 1 times v, and that will give me another point on the line. On the other hand, if I'd added, so before I do that, so this is saying t is equal to 1. If t is equal to 0, then actually I just end up at point P naught. If I, for example, take t equal to minus a half, then I start out from my point P naught and I go in the opposite direction, so I'm going to go like that, and I'm going to end up with this point over here. So this is saying t is equal to minus a half. So for all the different values of t, I add to my point P that multiple of my vector v, and that gives me the line. So just to summarize that, every point on this line has the position vector r, which is this bit here, equal to the position vector of the point on the line plus some scalar multiple of the direction. If we want to think about this in component form, if our point P naught has components x naught, y naught, and z naught, and our direction vector v has components a, b, c, then we would write the equation of the line as in vector form x, y, z is equal to x naught, y naught, z naught. So that's our position plus some scalar multiple of the direction vector. And here we have t as any element of real numbers. So this gives us a vector equation. We could also think about this in the point form, just slightly changing notation. The point on the line, the point x, y, z, is found by taking the point x naught, y naught, z naught, and adding some scalar multiple of the point a, b, c. So these are equivalent. You can use whichever one you like. So that version of the equation for a line in 3D looks quite similar to the version in 2D, but there are other ways that we can also write equations for lines in 3D. For example, we can split our vector equation into 3 scalar equations. So if you recall, our vector equation over here looked like this. Well, we can split this up into components, so we can take the x component of each of these things, and that will give us one equation, and this just tells us how to find x, so x is going to be equal to x naught plus a times t, and then we could look for the y component, and we'd end up with y is equal to y naught plus bt, and then finally we could have a look for our z component, and that would give us z is equal to z naught plus ct. So we've still got exactly the same information, except we've split this into three equations. An equation for x, and again recall that x naught and a are constants. The x component of the point is what varies, as does this t. So t is an element of real numbers. And then for y and z, we also have that y naught and z naught are all constants, and so are b and c. And any one of these three looks quite a lot like our y is equal to mx plus c equation. So let's use what we've got to find a vector equation and also the parametric equations for the line passing through the point 5, 1, 3 parallel to the vector I hat plus 4j hat minus 2k. So notice we have a point on the line over here, and we have a direction vector. So to answer question A, for our vector equation, we know that our points on the line with position vector x, y, z is given by the position of a point on the line, so 5, 1, 3, plus all the possible scalar multiples of the direction vector. And here I'm going to change from using I, j, and k hat to just writing this in component form. So that's going to be a 1, 4, minus 2. So you can find any point x, y, z on this line by picking a value of t and then calculating 5 plus 1 times t for the x value, 1 plus 4 times t for the y value, and 3 plus minus 2 times t for the z value. So that's our vector equation. We can also write this in parametric form, so this is when we split it up into three equations. Here we've got x is equal to 5 plus t, y is equal to 1 plus 4t, and z is equal to 3 minus 2t. And these two different ways of expressing the line have the same information. As a point of interest, we could also write our vector equation as r, which the vector r stands for x, y, and z on the line. And then we could use our basis vector, so over here, to say our x component is going to be 5 plus t in the I hat direction, and then we're going to add to that 1 plus 4t in the j direction, and 3 minus 2t in the k hat direction. Just another way of writing exactly the same thing. So the next part of the question asks us to find two other points on the line, and we know that to find any point on the line, we start at the point 5, 1, 3, and then we add some scalar multiple of the direction vector. So if we decide to take, for example, let's take t is equal to 1, then we can find the point x, y, z is going to be equal to our point on the line, the position vector that we have, plus 1 times 1, 4, minus 2. And if we work that out, that's going to give us the point 6, 5, and 1. And you could pick any other value of t that you like. For example, let's take t is equal to minus 2. Then we get the point x, y, z equal to 5, 1, 3 plus minus 2 times our direction. And so we're going to have 5 minus 2, which is 3, 1 minus 8, which is minus 7, and 3 plus 4, which is 7. So there's another point that lies on our line. And you can work out any values of t that you choose to find points on the line. So the final question here is we'd like to know at what point does the line intersect the xy plane? So visually what we've got happening here is we've got our coordinate system and we've got our line. I don't know exactly how it looks, but suppose it looks something like this. And what we want to find out is if we have a look at the xy plane, which is this plane here, we would like to find out where does this line cut the xy plane. And the trick here is to remember that the xy plane has z is equal to 0. So if we use, for example, our parametric equations, we're going to have, well, we know that x is equal to 5 plus t. That's not super helpful. Y is equal to 1 plus 4t. But now we know that we're going to, for our parametric equation for z, we must have that 0 is equal to 3 minus 2t, and this gives us a way of calculating t. So this tells us that t is equal to 3 over 2. And that means that we can now go back and use this to calculate our values for x and y. So this tells us that x must be equal to 5 plus 3 over 2, and y must be equal to 1 plus 4 times 3 over 2. And so finally we have, if we just calculate those, we've got x is equal to 6.5, y is equal to 7, and z is equal to 0. So the actual point that we're looking for is the point 6.570. So it's worth thinking about the difference between lines in 2 dimensions and 3 dimensions. Now we know that in 2 dimensions, so when we're working in R2, our options in terms of 2 lines is we can have the 2 lines intersecting, we can have the 2 lines being parallel and never intersecting, and the very special case where the 2 lines actually lie on top of each other, which is kind of a special case of the parallel. But if we are in 3 dimensions, then we actually have 3 possible cases. So we have the case where we have our 2 lines and they intersect, so that's the same, and we have the possibility that our 2 lines are parallel. So those are the same. So we've got, we intersect, and over here we're parallel. But then we have another option, which is that our two lines aren't parallel, but they also don't intersect. So here we're thinking of a situation where you have one line doing something like this, and the other line is doing something else, but it doesn't intersect. It passes way behind. There are different angles. And we call this lines that are skew. So we've added a third possible case, which can't happen in 2 dimensions, because if two lines aren't parallel, then they have to intersect somewhere. But in 3 dimensions, you have a possibility that your two lines might never intersect. So lines are skew if they're not parallel and don't intersect. Now we come to our third way of expressing equations for lines in 3D. So we've seen the parametric line equations. So this is where we split our vector equation up into 3 equations. And you'll notice that in each of these equations we have a common variable. We have a t. So we find what are called the symmetric equations by solving for t. So I'm first going to look at the case where a, b, and c are not equal to 0, and then we'll deal with the alternative to that a little bit later. So if our a, b, and c are not equal to 0, then we can solve each of these 3 equations from our parametric equations for t. So we'll get t from our first equation for x, we get t is equal to x minus x naught divided by a. So now you can see why I said a is not allowed to be equal to 0. Solving our y equation, we get t is equal to y minus y naught over b. And for z, we get t is equal to z minus z naught over c. So now we have 3 equations. The right-hand sides are all different, but the left-hand sides are all t, so we can equate these. So we get what are called the symmetric equations, which are x minus x naught over a is equal to y minus y naught over b, which is equal to z minus z naught over c. And this is called the symmetric equations. And you'll notice that in the symmetric equations we don't have t. So just to check that we know where all the variables are, we have x naught, y naught, and z naught, which are the coordinates of a point on the line. And then we have a, b, and c, which give us the direction of the vector, of the line. So the things that I've just highlighted are all constants, and our variables are x, y, and z. So we need to deal with the case if, for example, a is equal to 0, then how do we find the symmetric equations? Well, if a is equal to 0, then having a look at this equation over here, we've just got x is equal to x naught. So that's going to be one of the equations. And then we have the other 2 equations for y and z. As before. So it's slightly different. You have equations for y and z, and our x is a constant over here. So just to summarize, because we've done quite a lot, we have 3 ways of describing lines in 3 dimensions, and they all rely on 2 bits of information. They rely on knowing a point P on the line, which has position vector r0, and we rely on knowing about the direction the line goes in, which is some vector v. For the vector equation, I'm going to change this notation a little bit. I'm going to call this the position r. So this vector r is the xyz position vector of any point on the line, and the way we find that point on the line is by taking the position vector of the point on the line and adding multiples of the direction vector. So we have a vector equation, or we could write it out in component form. Any point xyz on the line is given by the position of a point on the line plus some multiple times the direction of the line. We can also split this up into parametric equations, where I've just pulled x, x0, and a out of our vector equation to give me an equation for the x component, and we've done similar things for y and for z. And then for symmetric equations, we just have a slightly different looking thing. We have 2 equalities, but again we are using x0, y0, and z0, and a, b, and c. So this is if a, b, and c are not equal to 0, and we saw how to deal with the case if a or b or z is equal to 0. So spend some time working through problems and making sure you're comfortable with each of these 3 ways of describing lines in 3D.